So my name is Veeraswamy, Senior Lecturer in Government Polytechnic, Nirmal, Department Electrical and Electronics Engineering. I am teaching 5th semester subject AC Motors. Subject code 18EE 502C. Main topic special motors. Subtopic working principle of stepper motor and related terms and applications. Stepper motor. The explosive growth of computer industry in recent years has meant an enormous growth too for stepper motors, because these motors provide the driving force in many computer peripheral devices, right? In many computer peripheral devices, we are using stepper motors. For moving a printer and driving a CD driver for a fan and a computer printing purpose, like that. Many computer peripherals we are using a stepper motor. This stepper motor, however, can perform continuous tasks outside the computer industry as well, right? Actually, in a computer industry, we will step by step operation, right? Outside the computer industry, right, the stepper motor, however, can perform countless tasks outside the computer industry as well, right? A stepper motor is an electromagnetic device. Stepper motor is an electromagnetic device designed to convert a series of input power pulses, that is digital pulses, into discrete angular movement, that is angular movements, one of each power pulses, for each and every pulse the motor moves one step. For giving one pulse, the motor moves one step. Second pulse, second step. Like that, the motor moves step by step. Right? The stepper motor is an electromagnetic device designed to convert a series of input power pulses, that is a digital pulses, into discrete angular movements, that is a discrete angular movements, one discrete angular movement, one for each power pulse. Depending on the design of the motor and its intended to use, the power pulses may consist of current pulses of the same polarity or alternate pulses of opposite polarity, right? The pulses we are using in the stepper motor, depending upon the design of the motor and its design and use. So we will use the power pulses may be consist of current pulses of the same polarity, or the sequential pulses may all be the sequential pulses may all be delivered to the same motor winding successively to different coils in the motor, right? Pulses do not have to be delivered at any fixed rate, right? The machine is capable of continuous rotation. We can give a continuous rotation, right? So once again I will repeat, a stepper motor is an electromagnetic device designed to convert a series of input power pulses, that is digital, into discrete angular movement, mechanical. This angular movement is a mechanical, discrete angular movement, one for each power pulse. Next, depending upon the design of the motor and its use, the power pulses, that is depending upon the design of the motor and its intended use, the power pulses may consist of current pulse of the same polarity or alternate pulses of opposite polarity. We have same polarity, current of the same polarity, or alternate pulses of opposite polarity. So the sequential pulses may all be delivered to the same motor winding or successively to different coils in the motor. Right? So pulses do not have to be delivered at any fixed rate. Again, it is very important point noted that the control has two elements. The number of pulses which determine the angle of rotation. Number of pulses which determine the angle of rotation, and the direction of data which determines the order in which the poles are excited. The two controls are there. Please remember the two important elements to control. That is the number of pulses which determine the angle of rotation. Number of pulses determine the angle of rotation, and the direction of data which determines the order in which the poles are excited. Suppose if you want to rotate in clockwise direction, the order may be A, B, C, D, like that. Suppose in anti-clockwise direction, the order may be C, A, D, A, like that. So that is the sequence of excitation, for rotation clockwise or anti-clockwise, right? And the number of pulses determines the angle of rotation, right? So they have two control elements are there: the number of pulses which determine the angle of rotation, and the direction of data which determines the order in which the pulses are excited. So next, there are three types of stepper motors are there. So one is shaded pole stepper motors. In that again we have two types: unidirectional motors and bidirectional motors. And the second type is a permanent magnet stepper motor with two windings. Right? In that again we have SLO-SYN synchronous motor, slow synchronous stepper motor. And second one is Hydon stepper motor, and third one is Airfax permanent magnet stepper motor. In the third category we have variable reluctance stepper motor. It's a very important thing, variable reluctance stepper motor. So in that again we have two types: variable reluctance stepper motors, number two Kirchhoff variable reluctance stepper motor. That means broadly we can say that only three types. So one is shaded pole stepper motor, second one is permanent magnet type stepper motor, and third one is a variable reluctance stepper motor. Generally we are using variable reluctance stepper motor. Generally permanent magnet stepper motor is also known as a synchronous, a continuous operation. We will get a continuous operation, slow synchronous stepper motors, right? In shaded pole stepper motor and permanent magnet stepper motors, another one is a variable reluctance stepper motor. And another important point is already discussed, that is the two types of controls are there. So one is the number of pulses which determine the angle of rotation, and the direction of the data which determines the order in which the poles are excited. The direction, angle of rotation and the direction. So the data which determines the order in which the poles are excited, right? So once again I will repeat. So what is a stepper motor? A stepper motor is an electromotive device designed to convert a series of input power pulses, that is a digital, into discrete angular movements, that is a mechanical. So one for each power pulses, right? And another important point is depending upon the design and depending upon the usage, the power pulses consist of current pulses of same polarity or opposite polarity of the same polarity, or alternate pulses of opposite polarity. Same polarity or opposite pulses of same polarity. This is a second important point, right? And right, and there are two controls are there. One is angle of rotation, and another one is the direction, right? Angle of rotation, another one is the direction. So angle of rotation determined by the number of pulses, right? And the direction is determined the data in which you have to excite the order, and next one is there are three main types of stepper motors are there. One is shaded pole stepper motor, and one is a permanent magnet type stepper motor, and third one is variable reluctance stepper motor, right? Next, so very important points to be discussed here: stepper motor terminology. So the common terminology to describe the operation of stepper motor is, first one, step. The angular rotation produced by the output shaft each time the motor receives a step pulse. What is step? One step. The angular rotation produced by the output shaft. Each time the motor receives a step pulse. So very important. What is a step in a stepper motor? What is step? The angular rotation produced by the output shaft, each time the motor receives a step pulse. Next, what is the step angle? The rotation of the output shaft caused each step measured in degrees, right? The rotation of the output shaft caused by each step measured in degrees. What is the step angle? The rotation of the output shaft caused by each step. It is measured in degrees. Step angle means it is measured in degrees. So it is caused by each step, produced by the shaft and caused by each step, right? That is the step angle. What is the step? The angular rotation produced by the each shaft at each time the motor receives a step pulse. Pratisar, each time, right? Every time the motor gives pulses. When pulses given to the motor, the rotor rotates. That is step by step rotation. One step. For first pulse, the rotor moves one step. For second pulse, another step, like that, right? So the shaft rotation, by each time the rotor receives step pulse. Step angle means simply the rotation of the output shaft caused by the each step measured in degrees. Simply measured in degrees. Next, steps per revolution. How many steps per revolution? For one revolution, right? The total number of steps required for the output shaft to make one complete revolution. How many steps are required? Suppose here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 steps for one complete rotation, right? How many steps are required for one rotation? Here 12 steps per one rotation. Steps per revolution, that is known as steps per revolution. Number of steps that the motor takes in one revolution. Steps per revolution means total number of steps required for the output shaft to make one complete revolution. For one complete revolution, how many steps are required? That steps are known as steps per revolution. The total number of steps required for the shaft to make one complete rotation, for one complete rotation, is known as steps per revolution. So very important one is steps per second. Steps per second. What is steps per second? The number of steps the motor takes in 1 second. In 1 second, how many number of steps it takes, the motor takes, that is known as steps per second. The number of steps that the motor takes in 1 second. In one, that is, total revolution is different, and per 1 second, for 1 second, number of steps required by the motor are steps that the motor takes in 1 second. Motor takes in 1 second. That is the steps per second. Another one is steps per revolution. Then what is the holding torque? What is holding torque? The torque required to rotate the output shaft a full step with the motor energized and in a standstill condition. What is the holding torque? What is the holding torque? The torque required to rotate the output shaft. What is the torque required to rotate the shaft? To rotate the output shaft to a full step with the motor energized and in a standstill condition. Okay. Simply holding torque means start, nothing but a starting torque. Right? Each and every time the motor will take a starting torque. Right? So the starting torque means the torque required to rotate the output shaft a full step, for one full step with the motor energized in a standstill condition. The motor is energized in a standstill condition. Right? That is known as holding torque. Next one is the step response. The time usually in milliseconds for the motor to make one complete step, that is known as step response. Step response means generally it takes very milliseconds. The time usually in milliseconds for the motor to make one complete step. The time required for the motor for one step to make one complete step is known as response. Step response. Step response means the time usually in milliseconds for the motor to make one complete step. To make one complete step is known as step response. Known as step response. Next, start without error rate. Start without error rate. The stepping rate at which a motor with no external load inertia can start and stop without losing a step. Without losing a step is known as start without error rate. Start without error rate. Generally, the motor is connected to the load, some load, because we get some inertia. Right? The stepping rate at which the motor with no external load inertia can start and stop without losing a step. Can start and stop without losing a step. That is known as start without error rate. Without load inertia, the motor can start and stop without losing a step. Without losing a step, the motor can start and stop. That is known as start without error rate. The sleeping rate, the stepping rate at which the motor with no external load inertia can start and stop without losing a step. Number of steps per second. Rate means divided by time with respect to time. So another most important one is the slew rate. The maximum steps the maximum step rate at which the motor will run under a rated load once the motor has started rotating. This is usually substantially greater than the start without error rate. Initially, start without error rate means without any load, the steps rate at which a motor with no external load inertia can start and stop without losing step. Suppose if it is loaded, that is known as slew rate. The maximum step rate at which a motor will run under a rated load once the motor has started rotating. This is usually a substantially greater than the start without error rate. Generally, it is greater than start without error rate, that is known as a slew rate. Next one is ramping. A control method used to vary the pulse rate to accelerate from 0 step to accelerates from 0 steps per second to the running rate, or from any step rate to a different rate, whether it is accelerating or deaccelerating. A control method used to vary the pulse rate to accelerate from 0 steps per second to the running rate, or from any step rate to a different rate, whether it is accelerating or deaccelerating. Is known as ramping. Right? So these are the terminology we will use in stepper motor. One is a step. Step means the angular rotation produced by the output of the shaft each time the motor receives a step pulse. What is the step angle? The rotation of the output shaft caused by each step measured in degrees is known as a step angle. So what is steps per second? The number of steps that the motor takes in 1 second. Number of steps taken by the motor in 1 second is known as steps rate. Steps per revolution means for one revolution, the total number of steps required are taken by the motor output shaft to make one complete revolution. Is known as steps per revolution. What is the holding torque? What is required for motor for each and every time? The holding torque. The torque required to rotate the output shaft to full step with the motor energized and in a standstill condition. Is known as holding torque. What is the step response? The time usually in milliseconds. Step response is generally in time with respect to time. The time usually in milliseconds for the motor to make one complete step. What is the time taken by the motor to complete one step? That is known as step response. The time generally in milliseconds is taken by the motor to complete one step is known as step response. And next very two important definition, that is a start without error rate and the slew rate. Start without error rate for without external load and slew rate for with load. The stepping rate at which a motor with no external load inertia can start and stop without losing a step. The motor can start and stop without load inertia. That is known as start without error rate. What is the slew rate? The maximum step rate. It is a maximum step rate at which a motor will run under a rated load once the motor has started rotating. This is usually substantially greater than the start without error rate. Last one is ramping. The control method used to vary the pulse rate to to accelerate from 0 steps per second to the running rate, or from any step rate to a different rate, whether it is accelerating or deaccelerating, right? So these are the terminology we will use in stepper motors, right? Then we will discuss very important thing, that is working principle of stepper motor, right? So before going to what is a stepper motor, a stepper motor is an electromagnetic device designed to convert a series of input power pulses into discrete angular movements. It's an electromagnetic device designed to convert a series of input power signals, pulses or digital pulses into angular movement, that is a mechanical movement, one for each power pulse, right? That is known as stepper motor. Just by giving a pulses, the motor moves one step, right? By converting pulses into angular movements, by giving electrical pulses, digital into angular movement, or discrete pulses or discrete movements is known as a stepper motor, right? So let us consider working principle. A variable reluctance stepper motor, represented schematically. We can observe that its representation schematically in the sheet, in the slide. One slide, there are two diagrams are there, right? There are three stator coils. We have the A, B, C. You can observe in the sheet, in the diagram A, B, C. There are three stator coils are phases. Located 120 degrees apart. We can observe A, B, C are located 120 degrees apart, right? Each winding or phase are located 120 degrees apart, spatially 120 degrees apart. That is equally spaced around the circumference. General circumference is 360 degrees. For each and every 120 degrees, we placed one winding. So that's why it is equally distributed around the circumference, right? The variable stepper motor, we can observe in the diagram. There are three coils are there, or phases located 120 degrees apart, that is equally spaced around the circumference, and it is uniformly distributed winding. So the rotor is a soft iron with 4 salient poles. We can observe 1, 2, 3, 4. Where there are 4 salient poles are there. Salient poles means projected poles, right? So 3 exciting coils or phases A, B, C. They are 120 degrees apart, right? That means they are equally spaced around the circumference. And the rotor is a projected poles. The rotor is of soft iron type and with 4 salient poles. We can observe in the diagram. So it is shown in figure. That is 1, 2, 3, 4. 1, 2, 3, 4. There are 4 poles and 3 windings. 3 phases, 3 windings, 4 pole stepper motor. Next, let us consider when phase A is excited. First phase A is excited. Observe the first pole A, B, C. 1, 2, 3, 4. 4 poles are generally 90 degrees apart. We can equally divided 4 poles means for each and every pole there is a 90 degrees spatially separated, right? Observed in the first diagram, pole A is exactly coincide with the coil A, right? 2 is some little bit away from the coil B, and 4 is little bit away from the from the pole, but 3 is far away from B and C, right? So when phase A is excited, then what happens? When phase A, because phase A is excited, right? So to the phase A, there are nearly 3 poles are there. One is pole A, another one is pole 2, another one is pole 4. But pole 1 is very near to phase A. So that's why the A will be attracted. The pole 1 is attracted by phase A. So, right, when A is excited, rotor 1 and 3 line up with the axis of phase A, in the axis of A, which is along the axis of phase A. 1 and 3 are will align in the axis of A, right? If now the coil B is excited, after that, if you excite the coil B is excited, and excitation is removed from coil A. Excite the first initial only, excite the coil A, right? After that, excite B coil. After excitation of B coil, you have to remove A coil. You have to remove the excitation of A. After giving excitation to B coil, you have to remove the excitation of A coil. Tell me which pole will be attracted by B winding, whether the 2 or 3. Which one? Generally 2. Why? Because 2 is very near to B when compared to 3. When compared to 3, 2 is very nearer. So, if the coil B is excited, then the excitation is removed from the coil A. The rotor will move 30 degrees clockwise to assume the position we can observe in the figure 2, right? After excitation of base B, only 2 will be attracted, right? 2 will be attracted by phase B. Then 2 and 4 will be aligned along the B axis. 2 and 4 will be aligned along the axis B, right? So when it is aligned to 2 and 4 are aligned to B, what happens, right? The pole A will be moved 30 degrees, exactly 30 degrees clockwise. The rotor will move 30 degrees initially at point A. Then 2 is attracted by what happens? It is moved by 30 degrees. At 30 degrees, by movement of 30 degrees, the 2 will be aligned to B, right? So generally the B will be at 60 degrees angle with the B, but 1 is only 30 degrees angle with the B. So that's why B will be attracted by the two pole, right? Automatically 1 also moves 30 degrees in clockwise direction. 2 moves in 30 degrees clockwise, automatically 1 also moves in clockwise direction, right? Next, while the coil B exerts a pull on the both 2 and 3. Generally, when we excite the coil B exerts a pull on both 2 and 3, but the attraction is much greater on 2 with 30 degrees away, whereas 3 is 60 degrees away. I already told that the 2 will be 30 degrees away, which is 30 degrees away, whereas 3 is 60 degrees away. Actually, the B can pull second pole and third pole, but only it attract only second pole. Why? Because it is 30 degrees away, but B pole is 60 degrees away. Thus, the direction of rotation is an anti-clockwise direction. If now coil C is energized, initially coil A is energized, next after that coil B is energized. So after that, if we energize the coil C, energize the coil C, right? When coil C is energized, what happens, right? After giving the excitation to coil C, we have to remove the excitation of coil B. After giving excitation to C, you have to remove the coil B. Then what happens? When it's removed, automatically there is no attraction between B and 2, right? So we observe in the second diagram, when 2 and 4 are aligned with a B, after giving a C excitation, right, B will be very near to C. B will be very near to C when compared to 4, right? To the coil C, there two poles are there, third pole and fourth pole. The third pole will be only just 30 degrees away, but fourth pole is 60 degrees away. Right? That's why the coil C or phase C will be attracted by the pole B, the pole 3, Then the pole 3 and pole 1 will be aligned along the axis of C, along the axis of magnetic pole, along the axis of phase C, Then again the rotor rotates further 30 degrees, right? The rotor will be moved another 30 degrees clockwise, So hence, if we supply current pulses to phases A, B, C, A, etc., the rotor will step 30 degrees each current pulse, requiring 12 pulses to complete one revolution. Right? Very, very nice. For 30 degrees, for one pulse, it rotates 30 degrees. Right? For 3 pulses, 30 plus 30 plus 30, 90 degrees. For 3 pulses, 90 degrees. So another 3 pulses, 90 degrees. Another 3 pulses, 90 degrees. Another 3 pulses, 90. 4 3 is 12. For giving a 12 pulses in the sequence, first A, B, C, again A, B, C, again A, B, C. First A, B, C. Then again A, B, C. In the sequence, if you give the pulses, then the rotor step by step rotate by 30 degrees in 12 pulses. In 12 pulses, the rotor will complete one revolution. The rotor completes in one revolution. Right? Next. Sorry. But in 12 pulses, it completes one revolution. Next. To assume no loss or gain, the coil B must be energized before the excitation is removed from coil A, and coil C must likewise be energized before the excitation is removed from coil B, right? In the previous case, we excited A, next excited B. After excitation or before excitation, you have to remove the A. Right? Suppose the coil B is energized before the excitation is removed from coil A and C. And coil C must be clockwise be energized before the excitation removed from coil B. If coil A de-energized before power is applied to B, that is torsion in the load coupling could turn the rotor counterclockwise just enough to that when motor was supplied to coil B, it will be attracted to poles 3 and 1. Suppose if you want to rotate the rotor in another direction, right, in anti-clockwise direction, then so first you give the excitation to A, after that give an excitation to C instead of B, give excitation to C. Then what happens? If you excited the C, what happens? So 4 is very near to C when compared to 3. Then the 4 will be attracted by C. Then the pole 1 will be rotated 30 degrees in anti-clockwise direction. Right? Simply by changing the sequence, and instead of A, B, C, we change the sequence A, C, B. Then what happens? The rotor rotation changes. Right? So it should be clear that if the pulses are applied to phase A, C, B, A, first A, next C, Next B, next A is D. The rotor will turn in counterclockwise direction. Rotor turns in counterclockwise direction, right? It also be shown that if the motor has 8 equally spaced teeth, suppose the motor has, instead of 4 teeth, 4 poles, suppose it is 8 teeth, suppose it has 8 teeth, the rotor would move only 15 degrees for each pulse. Because of 4 pulses, the rotor rotating 30 degrees, right? Suppose if it is a 8 pole, then the rotor would move 15 degrees for each pulse. That means requiring 24 pulses to complete one revolution. 24 pulses to complete one revolution. Right, 24 pulses are required. Clear? Suppose if it is a 3-phase 4 pole, right? So it requires 12 revolutions at 12 pulses for one complete rotation. One complete rotation will be 360 degrees. 360 by 30. 360 by 30 means it is equal to 12. We require 12 pulses. Suppose if it is a 4-pole machine. If it is a 4-pole machine, if the 3 phases are there, then what happens? For each and every excitation, what happens? The rotor will rotate only 15 degrees. So that's why it requires 360 by 15. That means 24 pulses are required. 24 pulses are required for one complete revolution. Right? So next, this is about working principle of a 3-phase induction. Stepper motor. Working principle of a stepper motor, right? So then, what are the main applications of a stepper motor? The stepper motor is a digital device. Its outputs being determined by the number of its pulses. Its output is determined by the number of output means rotation, steps, number of steps. Its output is determined by the number of pulses. The motor can position an object accurately on an input command in the form of a number of pulses. So provided it is used in the response range. Simplicity and economy are advantages of this motor together with the fact that it is a digital device and compatible with the computer outputs. Right? So the following are some important applications of the stepper motor. So one is remote indicator or positioner. Next, B will be second is XY plotter, X and Y coordinate pens, X and Y plotter. And third one is a machine tool positioner. If you want to position the machine tool for CNC machine, for mechanical purpose, if you want to machine tool position, that means for every but depending upon number of position, we can exactly position the machine tool, right? Digital feedback position control. And next one is dividing the paper feed mechanism in line printers and printing terminals. Driving the paper feed mechanism. Generally, you have some computers in the previous days. You have dot mac printers are there. In that case, simply the printer will rotate step by step, very slowly step. Each and every step the rotor, for after printing of one line, the motor must rotate for small angle. After printing another line, again you have to the roller will rotate for another step. So like that. So by giving input pulses, the rotor will rotate. After printing one line, the computer will give pulses to the stepper motor. The stepper motor rotate. After printing another line, by giving another pulses. Simply by giving a pulse, the rotor will rotate. Simply, so driving the paper feed mechanism in a printers and printing terminals and floppy disk drives. Generally, a floppy disk. So the floppy disk must be rotated. step by step, right? So in that case we will use a floppy disk drives to drive the floppy disk. So we will use the stepper motors. And military and mechanical applications, also we will use so this stepper motors, right? So today we will discuss what is the stepper motor. What is a stepper motor? Stepper motor is an electromagnetic device designed to convert a series of input pulses into discrete angular movements, one for each power pulse. That is a very important point. This is a definition. Next, depending upon the design and depending upon the usage, the power pulses may be consist of current pulses of the same polarity or opposite polarity. Same polarity or opposite. Another, there are two important to control terminals. That is number of pulses, which determines the angle of rotation, and the direction of data, which determines the order in which poles are excited, right? Next, what are the types? Three main types. One is shaded pole stepper motor. Second one is permanent magnet stepper motor. Right? And the third one is a variable reluctance stepper motor. And what are the main terminology? We will use step angle, step per second, step per revolution, holding torque, step response, slew rate, and start with without error rate, and ramping. These are the terminology we will use in the stepper motor. Next, in the working principle of stepper motor, we consider three phases and four poles. Four poles are the projecting poles, silent poles, right? And by giving a sequence of pulses A, B, C, A, like that, the rotor rotates in a clockwise direction. Suppose if the rotor, if want to rotate in anti-clockwise direction, then use a phase sequence of A, C, B. If you give A, C, B, then it rotates in anti-clockwise. If you give the sequence of pulses A, B, C, it rotates in clockwise direction, right? And one more important thing is, because of 4 poles, it rotates 30 degrees, then it requires 12 pulses. Suppose if it is 8 teeth, it has 8 teeth. For perception or perfection, it requires more number of steps. For smooth running, for best perfection, precision, we require number of poles must be there. We require number of poles. So when instead of 4 poles, if you use 8 poles, then the step angle will be 15 degrees. The step angle will be 15 degrees. Then we require 24 pulses. We require 24 pulses, right? So, thank you very much. Have a nice day.